Imagine this. There is no alarm, no countdown, no warning from scientists. 1 second, Earth is normal. The next, the planet is hit by the most powerful explosion the universe can produce, a gamma-ray burst. It does not arrive slowly. It does not give time to prepare. It travels at the speed of light, and when it reaches Earth, the damage is already done. In less than 10 seconds, more energy could strike our atmosphere than the Sun will produce in its entire lifetime. Satellites would be blinded. The upper atmosphere would ignite with radiation. Ozone would begin collapsing. Communication systems could fail worldwide. And most people on the surface would never even see it coming. Gamma-ray bursts are not theoretical. They happen across the universe right now, produced when massive stars collapse or when neutron stars collide and rip space-time apart. If one of these cosmic weapons were aimed directly at Earth, it would not cause an explosion on the ground. It would do something far worse. It would silently rewrite the chemistry of the atmosphere, destroy life support systems planet-wide, and trigger a chain reaction that could threaten civilization itself. In this documentary, we are going to explore what gamma-ray bursts really are, how powerful they truly become, and exactly what would happen minute by minute if one hit our planet without warning. We will look at real scientific data, past extinction theories, and the terrifying reality of how vulnerable Earth may be to cosmic events beyond our control. So if you want to understand one of the most dangerous forces in the universe, and why no planet is truly safe, subscribe now and stay with us. Because what you are about to hear is not science fiction. It is physics. And it is far more dangerous than most people realize.
Gamma-ray bursts are not just the most powerful explosions known to science. They are among the most extreme events the universe can produce. Brief flashes of radiation so intense that they can outshine entire galaxies for a few seconds. To understand what would happen if one struck Earth, we must first understand what a gamma-ray burst actually is. Despite the name, gamma-ray bursts are not single explosions like bombs. They are focused beams of energy released when matter is pushed beyond its physical limits. These beams are made of gamma radiation, the highest energy form of light. Unlike visible light, gamma rays carry enormous energy per particle, capable of breaking molecular bonds and altering atomic structures. There are two main types of gamma-ray bursts. The first type comes from massive stars that reach the end of their lives. When a star many times larger than our Sun runs out of nuclear fuel, its core collapses under gravity. In the most extreme cases, this collapse does not simply create a supernova. Instead, the core forms a black hole or a rapidly spinning neutron star, while powerful jets of energy erupt from the star's poles. These jets punch through the dying star and shoot into space at nearly the speed of light. When one of these jets is pointed directly toward Earth, we observe it as a long gamma-ray burst. The second type comes from the collision of neutron stars. Neutron stars are the collapsed cores of massive stars, packed so densely that a teaspoon of their material would weigh billions of tons. When two neutron stars orbit each other and eventually collide, the impact releases an enormous amount of energy in a fraction of a second. This creates a short gamma-ray burst, shorter in duration, but often just as powerful. Both types produce tightly focused beams. This is important. Gamma-ray bursts do not explode in all directions equally. They behave more like cosmic flashlights. Most of the energy is concentrated into narrow jets. That means Earth is safe from most gamma-ray bursts simply because the beams are not pointed at us. But if the alignment is perfect, the consequences change dramatically. A gamma-ray burst traveling through space does not slow down. It does not lose much energy. It crosses galaxies and interstellar voids almost untouched. When it finally reaches a planet, the impact is immediate. There is no physical object that arrives, no debris, no shockwave in space, only radiation. The first interaction happens high above the planet's surface. Earth's atmosphere becomes the first line of defense. When gamma rays strike the upper atmosphere, they collide with oxygen and nitrogen molecules. This collision produces cascades of secondary particles, high-energy electrons and photons, that spread downward through the atmosphere. In seconds, the upper layers of air become ionized, electrical charges build up, chemical reactions accelerate. The radiation does not directly burn cities or create firestorms. Instead, it triggers a chain of invisible reactions that alter the atmosphere itself. One of the most dangerous effects is ozone destruction. Earth's ozone layer protects life from harmful ultraviolet radiation from the sun. Gamma-ray bursts can break apart ozone molecules rapidly. Models suggest that a strong burst aimed directly at Earth could destroy a significant portion of the ozone layer in a short time. This would not be an instant extinction event, but it would begin a slow planetary crisis. With the ozone layer weakened, ultraviolet radiation from the sun would reach the surface in much higher amounts. This would damage plant life, disrupt ecosystems, and increase mutation rates in living organisms. Marine plankton, the foundation of ocean food chains, would be especially vulnerable. This alone could destabilize global ecosystems, but ozone loss is only part of the damage. Gamma-ray bursts also produce nitrogen oxides in the atmosphere. These chemicals contribute to long-term ozone depletion and can alter atmospheric circulation patterns. Some models suggest they could create global cooling effects by increasing atmospheric opacity, reducing sunlight reaching the surface. In other words, a gamma-ray burst could simultaneously expose Earth to more harmful radiation while also reducing surface temperatures. This combination would be devastating for agriculture and natural ecosystems. Technology would also suffer. Satellites in orbit would be hit first. Gamma radiation can damage electronic components, corrupt memory systems, and permanently disable sensitive instruments. Communication satellites, GPS networks, weather satellites, and Earth observation systems could experience widespread failure. This would disrupt navigation, financial systems, aviation, shipping, and global communications. Power grids on Earth could also be affected indirectly. High-energy radiation interacting with Earth's magnetic field could trigger geomagnetic disturbances. These disturbances can induce currents in long power lines, damaging transformers and causing blackouts. Modern civilization depends heavily on space-based infrastructure. A sudden collapse of satellite systems would ripple through nearly every sector of society. But the most unsettling part of gamma-ray bursts is not only the damage they cause, it is how little warning we would have. Unlike asteroids, which can sometimes be tracked years in advance, gamma-ray bursts occur without long-term visible build-up. The star collapse or neutron star collision happens far away, but the beam arrives at Earth at the speed of light. By the time instruments detect the burst, it has already arrived. There is no evacuation, no shelter, no global alert system that can stop it. The event would be over in seconds or minutes, but its consequences would last for years. Scientists believe gamma-ray bursts may have played a role in past mass extinction events on Earth. While this is still debated, some extinction periods show chemical signatures consistent with sudden atmospheric changes that could match gamma-ray exposure. Earth's location in the galaxy provides some protection. We are not near the dense star-forming regions where massive stars frequently collapse. This lowers the probability of a nearby gamma-ray burst, but it does not reduce the risk to zero. Over geological timescales, rare events become inevitable. The universe operates on immense timescales. What seems impossible in a human lifetime becomes likely over millions of years. This raises a deeper question. How safe is Earth, really? We often think of our planet as isolated and protected, but cosmic events do not respect planetary borders. Earth is part of a much larger cosmic system. Stars explode, galaxies collide, energy moves across unimaginable distances. Gamma ray bursts remind us that Earth is not shielded from the universe. It is simply lucky so far. In the next part, we will examine how far away a gamma ray burst would need to be to seriously harm Earth, what safe distance actually means in cosmic terms, and whether any known stars pose a realistic threat today. Because understanding distance is the difference between cosmic spectacle and planetary disaster. To understand how dangerous a gamma ray burst truly is, we need to answer a critical question. How close does it have to be to harm Earth? The universe is vast. Distances between stars are measured in light years. Most gamma ray bursts occur billions of light years away. From those distances, they appear bright to our telescopes but pose no threat to our planet. But distance alone does not determine danger. Power, beam direction, and duration all matter. Gamma ray bursts release enormous amounts of energy, but that energy spreads as it travels. The farther the burst, the more diluted it becomes. However, because the radiation is focused into narrow jets, the energy does not spread evenly in all directions. Inside the beam, the intensity remains extremely high over long distances. Scientists estimate that a gamma ray burst within a few thousand light years, if aimed directly at Earth, could cause significant atmospheric damage. A burst within a few hundred light years would be far more severe. At close enough range, it could trigger a global ecological crisis. To put this into perspective, our galaxy, the Milky Way, is about 100,000 light years across. That means dangerous events do not need to happen in our immediate stellar neighbourhood to affect us. Even explosions far from the centre of the galaxy could pose risks if their beams align perfectly. Fortunately, gamma ray bursts that come from massive star collapses tend to occur in regions of active star formation. These regions are often located in spiral arms and dense stellar clusters. Earth currently resides in a relatively quiet region of the Milky Way, far from the most intense star-forming zones. This lowers the probability, but again, probability is not zero. Some massive stars exist closer to Earth. A few of them are large enough to eventually collapse into supernovae or even gamma-ray bursts. The most commonly discussed example is a star called Eta Carinae. It is a massive star system located about 7,500 light-years away. While it is not expected to produce a gamma-ray burst aimed at Earth, its existence reminds scientists that powerful stellar explosions can occur within our galaxy. Another potential candidate often mentioned is WR104, a binary star system with a rotating dust structure that some researchers once speculated might align with Earth. Later studies showed that the alignment is not as dangerous as initially thought, but the discussion itself highlighted an important reality. We cannot always predict stellar collapse behavior with perfect accuracy. Gamma ray bursts from neutron star collisions add another layer of uncertainty. Unlike massive stars, neutron star mergers do not require special star-forming regions. They can occur anywhere in the galaxy, including relatively quiet areas. When two neutron stars spiral together over millions of years, the final collision produces a powerful burst with little external warning. These events are rare, but when they happen, they are violent. The gravitational waves produced by neutron star mergers can be detected by observatories like LIGO and Virgo. However, these signals are detected at the same time the gamma ray burst occurs, not before. This means detection does not provide advance warning. It simply confirms that the event has already happened. This lack of warning is one of the most unsettling aspects of gamma ray bursts. There is no early detection system that can predict exactly when a star will collapse into a burst-producing event. Scientists can identify massive stars that may one day explode, but they cannot determine the exact moment. A star can appear stable for centuries and then collapse suddenly. This unpredictability makes gamma-ray bursts fundamentally different from many other cosmic threats. Asteroids can be tracked. Solar storms can be forecast hours in advance. Gamma-ray bursts offer no such courtesy. If one happens and the beam is aligned with Earth, the event will already be over by the time scientists realize it has occurred. Another factor that determines danger is beam width. Gamma-ray burst jets are narrow, often only a few degrees wide. This means most of the universe is spared from any single burst, but it also means that if Earth happens to fall within that narrow beam, the exposure is concentrated and intense. It is a matter of alignment, cosmic coincidence, chance geometry. The Earth could be completely unaffected by a burst occurring nearby, or directly in the line of fire of a burst occurring far away. This randomness is what makes gamma-ray bursts difficult to evaluate in terms of risk. Over short timescales, the probability is extremely low. Over millions of years, the probability increases. This is where geological evidence becomes important. Scientists study ancient rock layers, fossil records, and chemical signatures to look for signs of sudden atmospheric changes that could be linked to cosmic radiation events. Some extinction events show unusual patterns, sudden drops in biodiversity, changes in nitrogen isotope ratios, evidence of ozone depletion. These clues do not prove gamma-ray bursts caused past extinctions, but they suggest that cosmic radiation events may have played a role in shaping Earth's biological history. If gamma-ray bursts have influenced life on Earth in the past, they could influence it again in the future. This does not mean extinction is inevitable. It means Earth exists within a dynamic cosmic environment that occasionally produces extreme events. Understanding this environment is essential for long-term planetary defense. Some scientists have proposed hypothetical protective strategies. Ideas include artificial magnetic shields around Earth or atmospheric reinforcement systems. These concepts are currently far beyond practical implementation. Protecting an entire planet from gamma radiation would require technology orders of magnitude beyond what humanity currently possesses. For now, Earth relies on natural defenses: atmosphere, magnetic field, distance, luck. Another question arises from this reality. If gamma-ray bursts are so dangerous, how does life exist at all? The answer lies in rarity and scale. While gamma-ray bursts are extremely powerful, they are also rare in any given region of space. Most galaxies experience them infrequently. Combined with the narrow beam geometry, the odds of direct exposure remain low on human timescales. Life on Earth has survived for billions of years despite cosmic hazards. This suggests that while gamma-ray bursts are dangerous, they are not common enough to prevent the long-term development of life. However, as civilization becomes more technologically dependent, vulnerability increases. Ancient ecosystems could recover slowly from atmospheric damage. Modern civilization depends on fragile systems, satellites, power grids, global communication networks. A gamma-ray burst does not need to wipe out all life to cause catastrophic consequences. It only needs to disrupt critical infrastructure. Civilization is more sensitive than biology. This creates a new layer of risk. Even a moderate gamma-ray event could cause widespread technological collapse without causing immediate mass extinction. This means the impact of gamma-ray bursts must be evaluated not only in terms of biology, but also in terms of societal resilience. How quickly could civilization recover from a global satellite outage? How long could power grids remain down? How would food distribution adapt to communication failures? How would governments respond? These questions are rarely discussed, but they are essential. Gamma-ray bursts represent a type of disaster that does not target cities directly. It targets the systems that make cities function. In this sense, the greatest danger is not immediate destruction, it is systemic collapse. This is why scientists continue studying gamma-ray bursts, not out of fear, but out of necessity. Understanding the probability, mechanisms, and effects allows better preparation. Improved space weather monitoring, stronger satellite shielding, redundant infrastructure, emergency response planning. These measures cannot prevent a gamma-ray burst, but they can reduce its impact. In the next part, we will examine what would happen in the minutes, hours, and days after a gamma-ray burst strikes Earth, how the atmosphere would change, how ecosystems would respond, and how civilization would experience the aftermath. Because the true danger of gamma-ray bursts is not only in the moment of impact, it is in what comes after. The moment a gamma-ray burst strikes Earth, the event itself is over almost as quickly as it begins. There is no explosion on the surface, no shockwave ripping across continents, no fireball rising into the sky. Instead, the real damage unfolds invisibly, layer by layer, starting high above the planet. Within seconds of impact, gamma photons slam into the upper atmosphere. These particles carry so much energy that they immediately begin tearing electrons away from air molecules. Nitrogen and oxygen atoms become ionized. Entire regions of the ionosphere light up with electrical activity. Satellites in orbit would register sudden spikes across radiation sensors. Many would enter emergency shutdown modes automatically. Some would fail before protective systems could react. At the same time, a cascade of secondary particles would begin raining downward. Gamma rays do not simply stop at the top of the atmosphere. When they collide with molecules, they generate showers of energetic electrons, positrons, and X-ray photons. These secondary particles penetrate deeper into the atmosphere, spreading the energy over wide regions of the planet. This process creates something similar to a planet-scale radiation storm. Communication systems would be the first to show signs of disruption. High-frequency radio signals rely on predictable ionospheric behavior. When the upper atmosphere becomes heavily ionized, radio waves scatter unpredictably. Long-range communication could collapse within minutes. Aviation systems that depend on satellite navigation would experience errors. Military and emergency communication networks could lose stability. But this is only the beginning. One of the most dangerous effects begins silently inside the chemistry of the atmosphere. Gamma radiation breaks apart molecular nitrogen, freeing highly reactive nitrogen atoms. These atoms rapidly combine with oxygen to form nitrogen oxides. These compounds act as catalysts that destroy ozone. The ozone layer is Earth's primary defense against ultraviolet radiation from the sun. When ozone molecules are destroyed, harmful UV light is no longer blocked effectively. Within days of a strong gamma-ray burst, atmospheric models suggest that ozone depletion could reach dangerous levels across large portions of the planet. This does not cause instant death on the surface. Instead, it initiates a slow planetary crisis. As sunlight continues to strike Earth, ultraviolet radiation intensity increases. Plants begin experiencing cellular damage. Photosynthesis efficiency drops. Crop yields decline, forest ecosystems weaken. Phytoplankton populations in the oceans, responsible for producing much of Earth's oxygen, become especially vulnerable. Marine ecosystems would suffer first. Phytoplankton live near the surface of the ocean where UV radiation penetration is strongest. A significant decline in plankton populations would disrupt entire food chains. Fish populations would drop. Ocean biodiversity would decrease. This would affect global food supplies. On land, agriculture would face growing challenges. Increased UV exposure damages plant DNA. Crops become more susceptible to disease. Growth rates slow. Food production declines gradually, not instantly, but steadily. At the same time, nitrogen oxides in the atmosphere can contribute to cooling effects. These chemicals absorb sunlight and alter atmospheric circulation patterns. Some models suggest that after a major gamma-ray event, Earth could experience short-term cooling, similar to a weak nuclear winter scenario. This combination, higher radiation exposure with reduced sunlight, creates unstable climate conditions. Weather patterns would become unpredictable, rainfall distribution could shift, growing seasons could shorten. Extreme temperature swings could become more common. Civilization would feel these effects within weeks to months. Food supply chains would be stressed. Energy demand would fluctuate. Health systems would face new challenges as skin cancer rates and radiation-related illnesses increase over time. But one of the most immediate technological consequences would be orbital infrastructure failure. Many satellites would be damaged permanently, solar panels would degrade, sensitive electronics would suffer irreversible radiation damage, navigation networks would lose accuracy, weather monitoring systems would fail, communication relays would drop offline. The loss of satellite infrastructure would not be temporary. Replacing satellites takes time, launch schedules, manufacturing capacity, financial resources. Modern civilization depends on satellites far more than most people realize. Banking systems rely on satellite timing. Global trade uses satellite navigation. Disaster response depends on satellite imaging. A sudden reduction in satellite coverage would disrupt global coordination. Power grids would face indirect stress. While gamma-ray bursts do not directly induce geomagnetic storms like solar flares, the secondary atmospheric effects could interact with Earth's magnetic field in unpredictable ways. Electrical disturbances could propagate through long transmission lines. Transformer damage could occur in extreme cases. This would create regional blackouts. Recovery would take time. Large transformers cannot be replaced quickly. They are custom built. Some take months to manufacture. This creates cascading infrastructure risk. The real danger of gamma-ray bursts is not that they wipe out civilization instantly. It is that they undermine the systems civilization depends on. Transportation, communication, energy, food distribution, healthcare. All of these systems rely on stable environmental and technological conditions. Gamma-ray bursts disrupt both. Another important factor is psychological impact. Humans would not see the gamma-ray burst itself. There would be no visible warning, but within hours, news of satellite failures, communication disruptions, and atmospheric anomalies would spread. Fear and uncertainty would rise. Governments would struggle to explain what happened. Scientific agencies would release technical reports that few people fully understand. Public confusion would grow, misinformation would spread rapidly. Social stability could be threatened. Panic buying, market instability, political tension, all could follow. This highlights an often overlooked aspect of cosmic disasters. The physical damage is only part of the problem. Human reaction is equally important. Civilization is not only built on infrastructure, it is built on trust. Trust in systems, trust in institutions, trust in information. Gamma-ray bursts challenge that trust. They introduce uncertainty on a global scale. Another long-term consequence is biological mutation. Increased radiation exposure raises mutation rates across many species. Most mutations are harmful or neutral, but over time, increased mutation pressure can accelerate evolutionary changes. This could alter ecosystems in unpredictable ways. Some species might adapt, others might decline, biodiversity patterns could shift. Human populations would also be affected. While the atmosphere blocks most direct gamma radiation, the indirect effects, increased UV exposure and secondary radiation, could increase long-term cancer risk. Medical systems would face growing strain. Public health challenges would evolve slowly but persistently. Gamma-ray bursts, therefore, represent a type of disaster that unfolds over years rather than days. The initial impact is brief. The consequences linger. They reshape the environment. They alter technology. They change biological systems. They stress societies. This is why scientists consider gamma-ray bursts to be among the most dangerous cosmic threats despite their rarity. Not because they produce dramatic explosions on Earth, but because they attack the foundation of planetary stability. Earth has survived many cosmic challenges in the past: volcanic supereruptions, climate shifts. Gamma-ray bursts represent another category of existential risk: rare, unpredictable, high impact. Understanding them is not about fear, it is about awareness. It is about preparation. It is about recognizing that Earth exists within a larger cosmic system that occasionally produces extreme events. In the next part, we will explore whether humanity could do anything to protect itself from a gamma-ray burst, what early detection systems exist, and whether planetary-scale defense is even possible. Because once we understand the danger, the next question becomes unavoidable: can we survive it? When facing a threat as powerful and unpredictable as a gamma-ray burst, the natural question becomes simple: can humanity protect itself? The honest answer is uncomfortable. There is no shield on Earth capable of blocking a direct gamma-ray burst. No technology currently exists that can stop high-energy photons traveling at the speed of light across cosmic distances. Unlike asteroids, which can theoretically be deflected, or solar storms, which can be forecast hours in advance, gamma-ray bursts offer almost no opportunity for intervention. The problem begins with detection. Gamma-ray bursts originate far beyond our solar system. When they occur, the radiation travels through space at light speed. There is no early warning phase that allows evacuation, shutdowns, or protective measures. Space observatories such as NASA's Swift and Fermi satellites monitor gamma-ray activity across the sky. They can detect bursts within seconds and relay their coordinates to scientists. But this system exists for research, not defense. It confirms what has already happened. It does not prevent it. Even if humanity somehow knew in advance that a specific star would collapse into a gamma-ray burst, predicting the exact timing would remain nearly impossible. Stellar collapse is chaotic. Internal processes inside massive stars can shift rapidly. A star that appears stable one day can collapse the next without visible warning signs. This unpredictability makes gamma-ray bursts uniquely dangerous. They are not gradual disasters. They are sudden cosmic events with delayed planetary consequences. Another idea often discussed in science fiction is planetary shielding. Could Earth be protected by an artificial magnetic field or energy shield? In theory, magnetic fields can deflect charged particles, like those from solar storms. But gamma rays are not charged particles. They are pure electromagnetic radiation. Magnetic fields do not deflect them. They pass straight through. To block gamma radiation, you need mass, very dense mass. On Earth, the atmosphere acts as our main shield. It absorbs much of the radiation and converts it into secondary particle showers before it reaches the surface. Without the atmosphere, life on Earth would be far more vulnerable, but thickening Earth's atmosphere artificially is not realistic. Building physical shields in space large enough to cover the planet is also far beyond current engineering capability. The scale required is enormous. Even if humanity devoted all global resources to such a project, it would likely take centuries to construct something capable of meaningful planetary protection. This leads to another uncomfortable truth. There is no practical way to defend Earth from a gamma-ray burst. The best protection is probability, distance, and luck. However, that does not mean humanity is completely helpless. While we cannot stop the burst itself, we can reduce vulnerability to its consequences. The most effective protection strategies focus on resilience, strengthening infrastructure, hardening satellites, building redundancy, preparing emergency response systems. These measures do not prevent damage, but they reduce collapse. Satellite hardening is one of the most important steps. Radiation-resistant electronics already exist. Space agencies design spacecraft components that can tolerate high radiation environments. Improved shielding, fault-tolerant systems, and redundant circuits can allow satellites to survive higher radiation exposure. Commercial satellite operators increasingly invest in radiation-hardened designs because space weather events already pose regular risks. These improvements indirectly increase resilience against extreme cosmic events. Another critical area is power grid protection. Geomagnetic storms already threaten electrical infrastructure. Some countries have begun reinforcing transformers and installing protective devices that reduce damage from induced currents. While gamma-ray bursts do not directly produce the same magnetic effects as solar storms, strengthening grid resilience improves overall disaster readiness. Communication redundancy is equally important. Diversifying communication networks reduces dependence on satellites alone. Fiber optic systems, ground-based relays, and regional networks provide backup options. If orbital systems fail temporarily, terrestrial communication infrastructure can maintain limited connectivity. Food system resilience is another concern. If gamma-ray bursts trigger ozone depletion and climate disruption, agriculture becomes vulnerable. Stockpiling food reserves, diversifying crop sources, and developing controlled environment farming methods could reduce long-term impact. Vertical farming, indoor agriculture, hydroponics. These systems operate independently of external weather conditions and could help stabilize food production during environmental disruptions. Medical preparedness also matters. Increased UV exposure and radiation-related health effects would require expanded healthcare capacity. Monitoring radiation exposure, early cancer screening programs, and improved treatment technologies would become more important. These are not direct defenses, they are survival strategies. Another concept explored by scientists is early warning detection of nearby high-risk stars. Astronomers can identify massive stars that may one day collapse. They can track binary neutron star systems that may merge. While exact timing cannot be predicted, risk assessment can be improved. Mapping potential gamma-ray burst progenitors allows scientists to estimate long-term risk patterns. It does not eliminate danger, but it improves awareness. Future space observatories may also detect gravitational waves and neutrino emissions that precede certain types of cosmic events. While these signals often arrive at the same time as gamma radiation, advancements in detection technology may eventually provide seconds or minutes of warning in rare cases. Even a few minutes could allow critical systems to enter safe mode. Satellites could shut down sensitive components. Power grids could isolate vulnerable transformers. Communication networks could switch protocols. This would not prevent atmospheric damage, but it could reduce technological collapse. The idea of planetary evacuation is unrealistic. Earth's population cannot be moved. Shelters provide limited protection. Gamma radiation penetrates most materials. Only deep underground environments offer significant shielding. In extreme scenarios, underground facilities might become temporary refuges for critical infrastructure and leadership, but this would not protect ecosystems or global populations. This highlights the scale of the challenge. Gamma-ray bursts are planetary-level events. They affect the entire biosphere. They are not localized disasters. They are global phenomena. Because of this, long-term planetary resilience becomes more important than short-term reaction. Humanity must treat cosmic hazards as part of environmental risk planning. Just as societies prepare for earthquakes, hurricanes, and pandemics, they must consider space-based threats. This requires education, public awareness, international coordination, scientific investment. Space agencies already collaborate on asteroid monitoring programs. Similar global cooperation could expand into cosmic radiation hazard research, shared data, unified response frameworks, joint infrastructure protection strategies. These steps build resilience across nations. Gamma-ray bursts also raise philosophical questions about control. Humans often assume that with enough technology, any problem can be solved. Cosmic events challenge this assumption. Some forces in the universe operate beyond practical human control. The goal is not dominance, it is survival. This shifts the narrative of space exploration. From conquering space to learning how to coexist with cosmic forces, accepting limits, working within physical laws, designing systems that tolerate risk. Another long-term possibility involves moving civilization beyond a single planet. Multiplanetary survival reduces extinction risk. If humanity establishes independent colonies on Mars, the Moon, or artificial space habitats, A gamma-ray burst affecting Earth would not necessarily wipe out the entire species. This concept of distributed civilization is often discussed in planetary defense circles, not as escape, but as redundancy. However, this strategy also introduces new radiation challenges. Mars lacks a strong magnetic field. The Moon has almost no atmosphere. Space habitats face continuous radiation exposure. Solving radiation problems becomes even more critical if humanity spreads outward. In this sense, gamma-ray bursts reinforce a central lesson. Survival beyond Earth requires deep understanding of cosmic hazards, not just engineering, not just ambition, but realistic risk management. Preparedness does not guarantee safety, but it increases survival odds. Gamma-ray bursts remind us that Earth exists inside a much larger system, a system shaped by stellar explosions, gravitational collisions, and energetic processes beyond human influence. We cannot stop these events, but we can choose how prepared we are when they occur. In the next part, we will explore whether gamma-ray bursts could be responsible for mass extinction events in Earth's past, and what geological evidence suggests about the role of cosmic radiation in shaping life's history. Because sometimes the greatest threats are not only in the future, they may already be written into the story of Earth itself. Long before humans built satellites, power grids, or cities, Earth had already experienced violent changes driven by forces far beyond its atmosphere. The planet's history is written in layers of rock, fossil records, and chemical signatures. Within those layers, scientists have discovered evidence of sudden environmental shifts that cannot always be explained by volcanoes, climate cycles, or asteroid impacts alone. This has led some researchers to ask a disturbing question: could gamma-ray bursts have influenced Earth's past? The idea is controversial, but it is taken seriously enough to be studied. Unlike asteroid impacts, gamma-ray bursts leave no physical crater. They do not deposit iridium layers, they do not scatter debris across continents, but instead they leave subtle chemical fingerprints, changes in atmospheric composition, shifts in isotopes, and patterns of biological collapse that match the effects of radiation exposure. One of the most discussed events in this context is the late Ordovician mass extinction, which occurred about 450 million years ago. During this period, nearly 85% of marine species disappeared. Unlike other mass extinctions, this event does not show strong evidence of asteroid impact or massive volcanic activity. Instead, it appears to be linked to sudden climate cooling and ozone depletion. Some models suggest that a nearby gamma-ray burst could explain these conditions. If Earth had been exposed to a powerful gamma-ray beam during that time, atmospheric ozone destruction could have increased ultraviolet radiation at the surface. Marine plankton populations would have collapsed. Food chains would have broken down. Climate feedback effects could have triggered global cooling. This does not prove a gamma-ray burst caused the extinction, but it shows that the mechanism is scientifically plausible. Another extinction event sometimes discussed is the late Devonian extinction, which occurred around 370 million years ago. This event involved multiple extinction pulses and prolonged environmental stress. Again, there is limited evidence of asteroid impact, but strong evidence of ecosystem disruption. Radiation-driven atmospheric changes remain one of several possible explanations. What makes gamma-ray bursts unique is how they operate. They do not destroy ecosystems through physical impact. They alter the planet's protective layers. They change the rules of survival rather than directly killing organisms. This is why their fingerprints are difficult to identify. Instead of dramatic geological scars, scientists look for sudden drops in biodiversity, shifts in nitrogen isotope ratios, evidence of ozone depletion, patterns of UV damage in fossilized plant spores, changes in sediment chemistry that reflect altered atmospheric circulation. These clues are subtle, they require careful interpretation, and they often overlap with other possible causes. This makes it difficult to prove direct links, but it also means gamma-ray bursts cannot be ruled out as contributors to Earth's evolutionary history. If gamma-ray bursts have affected Earth before, they may have influenced the direction of life itself. Mass extinctions do not only destroy species, they reshape ecosystems. They create evolutionary bottlenecks. They allow new species to rise and dominate. After the late Ordovician extinction, marine ecosystems reorganized. New groups of organisms expanded. Biodiversity eventually recovered, but the structure of life on Earth changed. This means gamma-ray bursts, if they occurred, may have indirectly shaped the path of evolution, not through deliberate design, but through environmental pressure. This adds a new dimension to how we understand Earth's relationship with the universe. Life on Earth may not be shaped solely by internal planetary processes. It may also be influenced by rare cosmic events. This challenges the idea that Earth is isolated from galactic activity. In reality, Earth exists within a dynamic galaxy. Stars are born, stars die, explosions release energy. Radiation travels across space. Occasionally, that energy intersects with planets. Earth is not immune. Another important factor is timescale. Gamma-ray bursts are rare on human timescales, but Earth's history spans billions of years. Over such long periods, even extremely rare events become statistically significant. A gamma-ray burst that occurs once every few 100 million years could still influence planetary history multiple times. This is why scientists study long-term cosmic hazard rates, not because they expect disaster tomorrow, but because they want to understand long-term planetary risk. This is similar to studying supervolcano eruptions or asteroid impacts. Rare events with massive consequences shape long-term survival strategies. Understanding these risks helps humanity develop realistic expectations about cosmic stability. It also influences the search for life elsewhere. If gamma-ray bursts can sterilize or severely damage planetary biospheres, this affects where life can persist in the galaxy. Galactic regions with frequent massive star formation may experience more gamma-ray bursts. Planets in those regions may face repeated radiation exposure. This could limit the development of complex life. Our location in the Milky Way, relatively far from the galactic center, may be one reason Earth has enjoyed long-term stability. The center of the galaxy is crowded, stars form rapidly, supernova rates are higher, gamma-ray burst probability increases. Earth's quiet neighborhood may not be accidental in terms of habitability. This suggests that galactic environment plays a role in determining where intelligent life can emerge. Not all star systems are equally safe. Some are exposed to frequent cosmic hazards, others enjoy relative calm. This concept is known as the galactic habitable zone. It defines regions of galaxies where conditions are favorable for long-term life development. Gamma-ray bursts are one of the factors that shape this zone. This has profound implications for the search for extraterrestrial intelligence. If gamma-ray bursts regularly disrupt biospheres in certain regions, intelligent civilizations may be rare in those areas. Civilizations may cluster in quieter galactic neighborhoods. This could help explain why we do not observe obvious signs of widespread advanced civilizations, not because life is impossible, but because survival over long timescales requires stable environments. Gamma-ray bursts add to the list of filters that life must pass through. Asteroid impacts, supernova radiation, stellar instability, climate cycles, all of these act as barriers. Only planets that survive these challenges long enough can develop complex life and technology. Earth appears to have passed many of these filters. So far, this perspective makes gamma-ray bursts more than just a threat. They become part of the cosmic selection process. Not intentional, not designed, but real. They influence which planets remain stable long enough to host advanced life. They shape the long-term distribution of civilizations in the universe. Another implication concerns future humanity. As humans expand beyond Earth, they will carry life into new environments. Colonies on Mars, moons, and space habitats will face different radiation risks than Earth. If gamma-ray bursts affect the entire solar system, Off-world colonies may be even more vulnerable due to weaker atmospheric and magnetic protection. This means that spreading humanity across multiple planets does not automatically eliminate gamma-ray burst risk. It redistributes it. Some colonies may survive better than others. Protection strategies will vary. Radiation shielding becomes essential for off-world survival. This reinforces the idea that cosmic hazards must be integrated into long-term expansion planning, not as secondary concerns, but as primary survival factors. Another lesson from Earth's past is resilience. Despite mass extinctions, life recovered, ecosystems rebuilt, biodiversity returned. Earth did not become permanently sterile. This suggests that even if gamma-ray bursts cause severe damage, life itself is remarkably persistent. Civilization, however, is more fragile. Human technology depends on stable conditions. Infrastructure cannot adapt biologically. Societies depend on coordination. Recovery from global disruption would be slow and complex. This creates a paradox. Life may survive gamma-ray bursts. Civilization may not. This makes preparedness even more important. Protecting knowledge, preserving technology, maintaining data archives, building resilient systems. These steps increase the chance that civilization could recover after a cosmic event. Gamma-ray bursts, therefore, represent not just a biological threat, they represent a civilizational challenge. They test the durability of human systems, they expose weaknesses in global coordination, they reveal dependencies that often go unnoticed. Studying Earth's past helps scientists understand these risks better. It provides context. It shows what has happened before. It reveals patterns of vulnerability and recovery. And it reminds humanity that cosmic forces have shaped Earth's history long before humans appeared. They will continue shaping it long after. In the next part, we will explore the long-term future, how often gamma-ray bursts are expected to occur, how risk changes as the galaxy evolves, and whether Earth's danger level will increase or decrease over time. Because survival is not only about the present, it is about understanding the future trajectory of cosmic risk. When we talk about gamma-ray bursts as a threat, it is natural to ask another critical question. Is this danger getting worse or better? The universe is not static. Galaxies evolve, stars are born and die. The conditions that produce gamma-ray bursts change over time. To understand Earth's long-term risk, scientists study how these cosmic processes shift across billions of years. In the early universe, gamma-ray bursts were far more common. Young galaxies were filled with massive stars. These stars burned quickly and collapsed violently. Star formation rates were much higher than today. This created ideal conditions for frequent gamma-ray bursts. As the universe aged, star formation slowed. Many of the largest stars that could produce gamma-ray bursts already lived and died. Modern galaxies, including the Milky Way, are calmer environments compared to the cosmic past. This is good news for Earth. It means that the overall frequency of gamma-ray bursts has decreased over time. However, this does not mean the danger has disappeared. Gamma-ray bursts still occur regularly across the observable universe. They are detected almost daily by space observatories. Most are far away and harmless to Earth, but the mechanisms that produce them remain active. Massive stars still exist. Binary neutron star systems still orbit and merge. Black holes still form. These processes ensure that gamma-ray bursts will continue to occur for billions of years. Within our own galaxy, the Milky Way, the risk is lower than in denser star-forming regions, but not zero. The Milky Way contains hundreds of billions of stars. Among them are many massive stars capable of violent collapse. There are also unknown numbers of neutron star pairs slowly spiraling toward collision. Astronomers estimate that a gamma-ray burst capable of seriously affecting Earth might occur in our galaxy once every several 100 million years. That timescale sounds comforting, but on geological timescales it becomes significant. Earth has existed for over 4 billion years. That means multiple opportunities for exposure have already occurred, and multiple opportunities remain in the future. This is not a short-term threat. It is a long-term background risk, one that operates quietly across deep time. Another factor influencing future risk is galactic motion. The solar system is not stationary. It orbits the center of the Milky Way once every 225 to 250 million years. During this journey, the solar system passes through different regions of the galaxy. Some regions are relatively quiet, others contain higher star density and increased stellar activity. As the solar system moves through spiral arms, star formation rates increase. This temporarily raises the probability of nearby supernovae and gamma-ray bursts. Some scientists believe Earth's mass extinction cycles may be partially linked to this galactic movement. Not proven, but plausible. If Earth periodically passes through more dangerous regions of the galaxy, cosmic hazards could increase during those times. This introduces a new dimension to planetary risk. Earth's safety is not constant. It fluctuates over cosmic timescales. Another factor is the evolution of Earth's own protective systems. Earth's magnetic field is generated by motion inside the planet's core. Over millions of years, this field changes strength and direction. Geological records show that Earth's magnetic poles have reversed many times. During reversals, the magnetic field weakens temporarily. This does not eliminate protection entirely, but it reduces shielding against charged particles. If a gamma-ray burst were to occur during a period of weakened magnetic protection, Earth could be more vulnerable to secondary radiation effects. Similarly, Earth's atmosphere is not fixed. Volcanic activity, climate cycles, and biological processes influence atmospheric composition over time. Periods of lower oxygen concentration or thinner ozone layers could increase vulnerability to radiation events. This means Earth's protection varies. It is strong today, but it may not always be equally strong in the distant future. Another consideration is humanity's own impact. As civilization expands into space, more infrastructure will exist beyond Earth's atmosphere. Satellites, space stations, lunar bases, Mars colonies. All of these systems will be directly exposed to cosmic radiation. A gamma-ray burst that causes moderate damage on Earth could cause severe damage to off-world settlements with weaker protection. This changes the risk profile. Human expansion increases exposure. At the same time, technological advancement increases resilience. Future spacecraft will be better shielded. Habitats will be designed with radiation protection in mind. Monitoring systems will improve. Emergency response strategies will evolve. This creates a race between vulnerability and preparedness. As humanity spreads outward, risk increases. As technology advances, protection improves. The balance between these two forces will determine future survival. Another important trend is scientific detection capability. Modern astronomy has dramatically improved our ability to observe gamma-ray bursts. Space telescopes can detect bursts across the universe. Gravitational wave observatories can identify neutron star mergers. Multi-messenger astronomy combines light, gravitational waves, and particle detection. This network provides deeper understanding of gamma-ray burst frequency, distribution, and behavior. Better data allows better risk modeling. Scientists can estimate probabilities more accurately. They can identify regions of higher hazard. They can track changes in galactic conditions. While this does not prevent gamma-ray bursts, it improves preparedness. Knowledge reduces uncertainty. Uncertainty is one of the most dangerous elements of disaster risk. Another factor shaping the future is planetary defense policy. Space agencies already invest heavily in asteroid detection and deflection programs. Similar efforts could expand into broader cosmic hazard monitoring. Dedicated gamma-ray observatories, advanced early detection systems, automated response protocols. These systems cannot stop gamma-ray bursts, but they can coordinate global response more effectively. For example, rapid detection could trigger automatic satellite shutdown procedures. Power grids could isolate vulnerable components. Communication networks could shift to backup modes. Governments could activate emergency management plans. This transforms a sudden disaster into a managed crisis. It does not eliminate damage, but it reduces chaos. Another long-term strategy involves preserving knowledge. One of the greatest dangers of global disasters is loss of information. Data centers, scientific archives, cultural records. These are vulnerable to infrastructure collapse. Some organizations already work on long-term data preservation projects, underground archives, distributed storage networks, physical data vaults. These efforts aim to ensure that knowledge survives even if civilization experiences disruption. In the context of gamma-ray bursts, this becomes even more important. A civilization that loses technology but retains knowledge can rebuild faster. One that loses both faces far greater difficulty. Gamma-ray bursts also influence long-term philosophical thinking about humanity's place in the universe. They remind us that Earth exists inside a cosmic environment shaped by violent processes. They show that stability is not permanent. They highlight the temporary nature of planetary safety. This perspective encourages humility. It challenges the idea that humans can control all variables. Instead, it suggests that survival depends on adaptation rather than domination. Another important implication is the value of planetary diversity. Some planets may be naturally better protected from radiation, thicker atmospheres, stronger magnetic fields, different orbital positions. Understanding these differences could guide future colonization strategies. Humanity may prioritize worlds with better natural shielding. This becomes part of long-term survival planning. Gamma-ray bursts also remind us that cosmic danger is not evenly distributed. Some regions of the galaxy are safer than others. Some time periods are safer than others. Understanding this spatial and temporal distribution becomes critical for future exploration. It informs where humanity builds permanent settlements, where it invests resources, where it concentrates population. The long-term future of civilization may involve strategic positioning within the galaxy. Not just technological expansion, but environmental optimization. Another subtle effect is psychological. Knowing that such powerful cosmic threats exist changes how people perceive security. It expands the scale of risk beyond Earth. It forces humanity to think on cosmic timescales. It encourages a broader perspective on survival. This may influence education, culture, and science priorities. The more humans understand the universe, the more they realize how rare, stable conditions truly are. Gamma-ray bursts represent one of the extreme expressions of cosmic instability. They are not frequent enough to dominate daily planning, but they are significant enough to influence long-term strategy. They belong in the same category as asteroid impacts and supervolcano eruptions. Rare, high impact, existential level risks. This is why scientists classify them as low probability, high consequence events. Such events require special attention, not panic, but preparation. Another factor shaping future risk is stellar evolution. As the universe ages, massive star formation will continue to decline. This gradually reduces gamma-ray burst frequency. In the far future, galaxies will contain fewer massive stars capable of producing these events. This suggests that long-term cosmic danger from gamma-ray bursts will slowly decrease. However, neutron star mergers will continue for billions of years. These systems take long time periods to spiral together. They ensure that gamma-ray bursts will not disappear entirely. So while the universe may become quieter, it will never become completely safe. There will always be cosmic hazards. This reality reinforces a central lesson. Humanity cannot wait for the universe to become safe. It must learn to survive in an unsafe environment. Preparation, resilience, adaptation. These become core survival strategies. In the next part, we will examine how humanity could respond socially, politically, and technologically after a gamma-ray burst event, how governments might react, how societies might reorganize, and what recovery could realistically look like. Because surviving the initial impact is only the first step, what happens next determines the fate of civilization. If a gamma-ray burst were to strike Earth and trigger widespread atmospheric disruption and technological collapse, the first days would not be defined only by physics, they would be defined by human reaction. How societies respond in the aftermath would determine whether civilization stabilizes, fragments, or descends into long-term crisis. In the first hours after impact, confusion would dominate. There would be no explosion to point at, no crater to analyze, no visible sign in the sky explaining what just happened. What people would see instead are failures. Navigation systems malfunctioning, communication satellites dropping offline, internet slowdowns or blackouts, power fluctuations, weather monitoring disruptions. Governments and scientific agencies would begin issuing statements based on incomplete data. Space agencies would detect unusual radiation patterns and atmospheric changes. News outlets would report unexplained global satellite failures before the true cause was fully understood. This information gap is dangerous. When people do not understand what is happening, fear spreads faster than facts. Social media would amplify rumors. Some would claim it was a cyber attack. Others would suspect nuclear activity. Conspiracy theories would appear almost immediately. Panic buying would begin in major cities. Fuel stations would fill. Supermarkets would empty. Markets would react violently. Stock exchanges rely on high-speed data and satellite timing systems. Disruptions could force temporary trading halts. Currency markets would become unstable. Investors would rush towards safe assets. Global supply chains, already sensitive to disruptions, would experience delays. Transportation systems would face serious challenges. Air travel relies heavily on satellite navigation and real-time communication. Many flights would be grounded. Shipping routes would experience navigation issues. Port operations could slow. Logistics companies would struggle to coordinate deliveries. This would directly affect food distribution. Modern cities depend on constant supply deliveries. Even short disruptions can cause shortages. With satellite failures and communication problems, coordination between producers, transporters, and retailers would break down. Governments would activate emergency response protocols. National emergency agencies would coordinate disaster management efforts. Military logistics units might be deployed to assist with supply distribution. Strategic reserves of food and fuel would be released in some regions. International cooperation would become critical. No single country could manage the aftermath alone. Atmospheric effects would be global. Satellite failures would affect every continent. Space agencies would share data. Governments would coordinate response strategies through international organizations. However, political tensions could also increase. Some nations might accuse others of causing the event. Even though gamma-ray bursts are natural, misinformation could trigger diplomatic conflicts. Trust between countries would be tested. Public communication would become one of the most important tools. Clear, transparent messaging from scientific authorities would be essential to prevent panic. Explaining that the event was cosmic in origin and outlining realistic expectations for recovery would help stabilize public response. But communication itself might be limited by infrastructure damage. This creates a dangerous feedback loop. The less people understand what is happening, the more fear grows. Increased ultraviolet exposure following ozone depletion would raise risks of skin damage and eye injury. Hospitals would need to adjust protocols. Public health agencies would issue new guidelines about outdoor exposure. Protective measures such as limiting sunlight exposure during peak hours, wearing protective clothing, and using UV blocking materials would become more important. Mental health would also be affected. Uncertainty, fear, and prolonged disruption create psychological stress. Anxiety disorders, depression, and trauma-related symptoms would increase. Governments would need to support mental health services alongside physical disaster response. As weeks pass, the focus would shift from emergency response to stabilization. Power grid repairs would become a priority. Satellite replacement planning would begin. Communication networks would be gradually restored using backup systems and terrestrial infrastructure. This phase would be slow. Launching new satellites takes months or years. Manufacturing delays would occur, insurance claims would flood the aerospace industry, companies would face massive financial losses. Some services might never fully return to pre-event capacity. This would force societies to adapt. Alternative navigation methods might be revived. Ground-based radio communication could become more important. Local supply networks might expand to reduce dependence on global logistics. This adaptation phase would reveal which societies are most resilient. Countries with diversified infrastructure, strong emergency management systems, and social cohesion would recover faster. Those with fragile systems and internal conflict would struggle. Another major challenge would be food production. If agriculture is disrupted by climate effects and increased radiation exposure, governments would need to support farmers aggressively. Emergency farming techniques could be implemented. Greenhouses, indoor farms, controlled environment agriculture, urban farming. These methods reduce dependence on outdoor conditions and could stabilize food supply in affected regions. Energy systems would also require adjustment. If power grids suffered damage, decentralization could accelerate. Local renewable energy systems such as solar microgrids and wind farms could provide partial independence from large centralized grids. This could permanently reshape energy infrastructure. In some ways, the aftermath of a gamma-ray burst could accelerate technological and social transformation. Crisis often forces innovation. Systems that fail reveal weaknesses. New solutions emerge. This does not make the event beneficial. It makes adaptation necessary. Another important aspect is governance. During prolonged crisis, governments face pressure to increase control to maintain order. Emergency powers may be expanded. Surveillance systems may increase. Restrictions on movement and trade could be implemented. This creates tension between security and freedom. Societies would have to decide how much authority to grant governments during recovery. These decisions could shape political systems for decades. International relations would also change. Countries with stronger space infrastructure and scientific capabilities would play leading roles in recovery efforts. New alliances could form around space monitoring and planetary defense cooperation. Space agencies might receive increased funding and political influence. Public interest in space science would rise dramatically. People would demand better understanding of cosmic threats. Education systems might place greater emphasis on astronomy, physics, and planetary science. Another long-term consequence is cultural shift. Humanity's perception of safety would change. The idea that Earth is isolated and protected would no longer feel absolute. Awareness of cosmic vulnerability would become part of collective consciousness. This could influence art, media, philosophy, and public discourse. The universe would no longer feel distant. It would feel present. Another major challenge is rebuilding trust in technology. After widespread satellite and infrastructure failures, people might lose confidence in digital systems. Cash transactions could temporarily increase. Local communication networks might be preferred over global platforms. Over time, as systems are rebuilt, trust would slowly return, but the psychological impact would remain. This is similar to how societies change after large natural disasters. Even after recovery, behavior patterns shift, preparedness increases, emergency planning becomes more common, risk awareness grows. In the long term, humanity might implement permanent planetary defense strategies, expanded space monitoring networks, dedicated cosmic hazard research programs, global emergency coordination frameworks. These would not prevent gamma-ray bursts, but they would improve response capability. Another possible outcome is increased investment in off-world infrastructure. Some may argue that spreading civilization across multiple planets reduces extinction risk. This could accelerate Mars colonization projects and space habitat development. However, as discussed earlier, off-world settlements face even greater radiation exposure. This would require heavy investment in shielding technology and habitat design. Still, the idea of becoming multi-planetary would gain political and public support. The aftermath of a gamma-ray burst would therefore not only be a recovery process, it would be a turning point, a moment when humanity re-evaluates its relationship with space, its dependence on fragile systems, its preparedness for cosmic risk, and its long-term survival strategy. One of the most important lessons would be the value of cooperation. No single nation could recover alone. Shared data, shared resources, shared technology. These would become essential. This could strengthen international institutions focused on space and disaster response, or, in worst cases, deepen geopolitical divides if cooperation fails. Which outcome occurs depends on leadership, communication, and public trust. The difference between collapse and recovery often lies not in technology but in coordination. This is why gamma-ray bursts represent not only a physical threat, they are a test of civilization itself, a test of adaptability, of cooperation, of resilience, of decision-making under uncertainty. The universe does not wait for humans to be ready. When humanity confronts a threat as vast and indifferent as a gamma-ray burst, something deeper than infrastructure damage begins to shift. It is perspective. For most of history, humans believed danger came from Earth itself. Storms, earthquakes, predators, wars. Space was distant, abstract, and largely irrelevant to daily survival. Gamma-ray bursts destroy that illusion. They reveal that Earth is not only shaped by forces beneath our feet, but by forces far beyond our sky. This realization carries profound philosophical weight. It challenges the idea that humanity is in control of its environment. On Earth, technology has allowed humans to dominate landscapes, redirect rivers, reshape ecosystems, and build cities that defy geography. But a gamma-ray burst reminds us that no matter how advanced civilization becomes, it still exists inside a universe governed by laws far older and more powerful than human invention. This is not weakness, it is reality. Understanding this can lead to two very different reactions: fear or humility. Fear leads to paralysis and denial. Humility leads to preparation and adaptation. The difference between the two may determine humanity's long-term survival. Gamma-ray bursts highlight the limits of prediction. Modern science can model stars, calculate probabilities, and simulate cosmic events, but it cannot predict the exact moment a massive star will collapse or two neutron stars will merge. There will always be uncertainty. This uncertainty forces a shift in how humans approach risk. Instead of trying to eliminate all danger, civilization must learn to manage uncertainty itself. That means building systems that can fail safely, designing infrastructure that degrades gracefully instead of collapsing catastrophically, creating social systems that remain stable under stress, developing communication strategies that prevent panic, teaching populations how to respond to rare but extreme events. In this sense, gamma-ray bursts become a lesson in resilience, not just technical resilience, but psychological and cultural resilience. Another deep implication involves humanity's sense of significance. People often ask whether humans matter in a universe so vast. Gamma-ray bursts make this question uncomfortable. They demonstrate how small Earth is compared to cosmic forces. A single distant star collapsing can release more energy in seconds than the Sun will produce in billions of years. From a cosmic perspective, Earth is fragile, yet this fragility does not make humanity meaningless. It makes survival remarkable. The fact that life exists at all in such a violent universe is extraordinary. The fact that intelligence evolved to understand these forces is even more remarkable. Gamma-ray bursts therefore highlight both vulnerability and uniqueness. They show how rare, stable conditions truly are. They show how precious Earth's protective systems are. They show how unlikely complex life may be in the broader universe. This perspective can change how humanity values its home planet. Earth is not just a resource to exploit. It is a shelter that allows consciousness to exist. Protecting it becomes not only an environmental responsibility but a cosmic one. Another philosophical shift involves the concept of destiny. Some people believe humanity is destined to become a spacefaring civilization, spreading across the stars. Gamma-ray bursts complicate this vision. They remind us that the universe is not an open frontier waiting to be settled. It is a hazardous environment that demands respect. Expansion will not be easy. It will not be fast. It will not be guaranteed. Every step beyond Earth increases exposure to radiation, vacuum, and cosmic danger. This does not make expansion impossible. It makes it conditional. Conditional on preparation, on technology, on cooperation, on patience. It also raises ethical questions about risk. Should humanity expose future generations to cosmic hazards in the pursuit of expansion? Who decides acceptable risk levels? What obligations do present generations have toward future settlers? If off-world colonies face higher radiation exposure, is it ethical to encourage permanent habitation? These questions will become increasingly important as space travel becomes more accessible. They force society to confront uncomfortable trade-offs between ambition and safety, between exploration and protection, between progress and responsibility. Gamma-ray bursts also influence how humanity views time. Cosmic timescales dwarf human lifespans. Stars evolve over millions of years, galaxies change over billions. Gamma-ray bursts are rare on short timescales, but inevitable over long ones. This perspective encourages long-term thinking. It challenges the culture of immediacy, short-term profit, short-term politics, short-term convenience. Survival in a universe with rare catastrophic events requires long-term planning. It requires investment in systems that may not show immediate returns, planetary defense programs, scientific research, education, infrastructure resilience. These are slow investments, but they build future security. Another philosophical impact is the relationship between randomness and order. Gamma-ray bursts are unpredictable in timing and location. They represent cosmic randomness, yet their behavior follows precise physical laws. They are chaotic events governed by structured processes. This reflects a deeper truth about the universe. It is both ordered and unpredictable, structured and chaotic, stable and violent. Human civilization must learn to operate within this dual nature, not expecting perfect safety, but designing systems that tolerate uncertainty. This mindset may extend beyond space hazards. It can influence how societies handle pandemics, climate change, economic instability, natural disasters. Gamma-ray bursts become part of a larger lesson about complexity and risk. They show that extreme events do not need to be frequent to be important. They only need to be possible. Another implication concerns identity. If humanity experiences a cosmic disaster, it may reshape how people see themselves, not as citizens of individual nations, but as inhabitants of a shared planet. When a threat affects the entire Earth simultaneously, national borders lose significance. Survival becomes collective. This could strengthen global cooperation, or it could intensify conflict if resources become scarce. Which outcome occurs depends on leadership and cultural values. Gamma-ray bursts therefore become a test of human unity. They ask whether humanity can act as a single species when faced with cosmic risk. Another layer of meaning involves scientific curiosity. Understanding gamma-ray bursts is not just about defense, it is about understanding the universe itself. These events reveal extreme physics, the behavior of matter under intense gravity, the formation of black holes, the nature of relativistic jets, They provide insight into fundamental laws of nature. Studying them advances knowledge far beyond planetary defense. It deepens understanding of energy, time, and space. This reinforces the importance of science funding and education, not as luxury pursuits, but as survival tools. Knowledge reduces vulnerability. Ignorance increases risk. The more humanity understands cosmic processes, the better it can prepare. Another philosophical shift involves the concept of control. Modern society often assumes technology provides control over the environment. Gamma-ray bursts expose the limits of that control. They show that some forces cannot be stopped, only endured, only managed. This does not mean surrender. It means redefining success. Success becomes resilience rather than dominance, survival rather than conquest, adaptation rather than control. This mindset may shape future technological development. Instead of building systems optimized only for efficiency, engineers may prioritize robustness. Instead of maximizing speed, designers may prioritize safety. Instead of centralized infrastructure, planners may favor distributed networks that are harder to collapse. Gamma-ray bursts push civilization towards a resilience-oriented design philosophy. Another subtle effect is cultural storytelling. Human myths and stories often involve gods throwing lightning or fire from the sky. Gamma-ray bursts represent a real cosmic equivalent, a force beyond human control. Understanding this may influence how humanity tells stories about the universe, not as a friendly backdrop, but as a dynamic environment filled with both beauty and danger. This can deepen respect for cosmic forces, not fear-based superstition, but informed awe, a recognition of scale, power, complexity. In the end, gamma-ray bursts remind humanity of something fundamental. Existence is not guaranteed. Life persists because conditions align, because protection exists, because stability happens to last long enough. This does not make life fragile in a negative sense. It makes it precious, worth protecting, worth understanding, worth preserving. Survival in a universe filled with rare but extreme events is not about avoiding danger entirely. It is about learning how to live with uncertainty, how to prepare for unlikely outcomes, how to recover from disruption, how to cooperate across boundaries, how to think beyond individual lifetimes. In the final part, we will bring everything together, the science, the danger, the human response, and the future, and answer the ultimate question: if a gamma-ray burst can strike without warning and without mercy, what does that mean for humanity's long-term destiny in the universe? And are we truly prepared to face a cosmos that does not care whether we are ready or not? When we step back and look at everything gamma-ray bursts represent, their power, unpredictability, and potential to reshape entire planets, one truth becomes clear: humanity does not exist in isolation. We are part of a much larger system, one that operates on scales of energy and time far beyond everyday experience. Gamma-ray bursts are reminders that the universe is not only beautiful and mysterious, it is also violent and indifferent. Yet, within this reality there is something uniquely human: the ability to understand, the ability to prepare, the ability to choose how to respond. This is where the story of gamma-ray bursts becomes more than astrophysics. It becomes a story about civilization itself. If a gamma-ray burst were to strike Earth tomorrow, it would test every layer of human organization, not just technology, not just infrastructure, but values, trust, leadership. The outcome would not be determined solely by radiation levels or atmospheric chemistry. It would be shaped by human decisions. How quickly governments coordinate, how transparently scientists communicate, how responsibly media outlets report, how calmly populations respond. Disaster history shows that societies with strong social cohesion recover faster than those fractured by mistrust. This pattern would likely repeat after a cosmic event. Gamma-ray bursts would expose inequalities. Some regions would recover faster than others. Countries with advanced infrastructure and emergency planning would adapt more effectively. Poorer regions would face greater challenges. This creates ethical responsibilities. If the threat is global, response should be global. International aid, technology sharing, scientific collaboration, these would become moral imperatives, not optional gestures. Another major question concerns long-term rebuilding. After the initial chaos stabilizes, humanity would face choices about what kind of civilization to rebuild. Should systems be restored exactly as they were, or should vulnerabilities be corrected? Crisis often creates opportunity for structural change. Energy systems could shift toward decentralization. Communication networks could become more resilient. Urban design could incorporate disaster-resistant architecture. Space infrastructure could be redesigned with higher radiation tolerance. This rebuilding phase would shape the future of civilization for generations. Another long-term consideration is memory. How will humanity remember such an event? Would it be treated as a rare anomaly, or as a permanent reminder of cosmic vulnerability? Collective memory influences preparedness. If societies forget quickly, investment in planetary defense may fade. If memory is preserved through education and culture, long-term resilience increases. This is why documentation matters. Scientific records, historical accounts, cultural storytelling all contribute to how future generations understand cosmic risk. Gamma-ray bursts also influence humanity's relationship with science. After experiencing a cosmic disaster, public trust in scientific institutions would become even more important. People would look to scientists for explanation, guidance, and reassurance. This places responsibility on scientific communication, not just accuracy, but clarity, accessibility, transparency. Science cannot remain isolated in academic circles. It must become part of public understanding. Another important issue is psychological adaptation. Living with the knowledge that rare but catastrophic cosmic events are possible changes human mindset. Some people may develop fatalism, others may develop hypervigilance. Healthy adaptation requires balanced awareness, acknowledging risk without becoming paralyzed by it. This is similar to how societies adapt to earthquake zones or hurricane regions. They accept risk while improving preparedness. Over time, gamma-ray bursts may become part of global risk education, taught in schools, included in emergency planning, integrated into disaster simulations, not as a source of fear, but as part of planetary awareness. Another long-term impact is technological prioritization. Funding may shift towards space monitoring, radiation protection, and planetary resilience technologies. Advanced materials, radiation-resistant electronics, energy storage systems, artificial intelligence for disaster response coordination. These technologies have benefits beyond cosmic defense. They improve everyday infrastructure resilience. This creates a positive feedback loop. Preparation for rare events strengthens systems for common challenges. Another major question involves human expansion beyond Earth. If gamma-ray bursts represent unavoidable cosmic risk, spreading civilization across multiple locations may become more attractive, not as escape, but as diversification. A multi-planet species is harder to wipe out completely. However, this strategy requires careful planning. Not all environments are equally safe. Mars lacks strong radiation protection. The Moon has no atmosphere. Space habitats require heavy shielding. Colonization must be designed with radiation risk in mind. Otherwise, expansion simply transfers vulnerability. Another philosophical layer involves meaning. In a universe capable of producing gamma-ray bursts, what gives human life value? Some argue that cosmic indifference makes life meaningless. Others argue the opposite. That meaning becomes stronger precisely because existence is fragile. That survival is not guaranteed. That consciousness is rare. From this perspective, understanding cosmic danger does not diminish humanity. It elevates the importance of protecting life, protecting knowledge, protecting future generations. Gamma ray bursts also force humanity to confront its temporal limits. Civilizations rise and fall, stars live and die, galaxies evolve. Nothing is permanent. This does not make effort pointless, it makes it significant. Every generation contributes to a long chain of survival. Each improvement in resilience increases the probability that future generations will exist. This long-term perspective encourages responsibility beyond individual lifetimes. Another important aspect is storytelling. Human culture often frames progress as linear. More technology, more power, more control. Gamma ray bursts challenge this narrative. They show that progress does not eliminate vulnerability, it changes its form. New technologies create new dependencies. Satellites increase connectivity but create reliance on space infrastructure. Digital systems increase efficiency but create fragility. Understanding cosmic risk encourages more thoughtful progress. Not just faster, but safer. Not just bigger, but more robust. This mindset shift could influence how humanity designs future systems. From cities to transportation, to global communication, to space exploration. Gamma ray bursts also reveal something about cosmic fairness. The universe does not target specific civilizations. It does not judge morality. It does not discriminate. It simply follows physical laws. This randomness can feel unfair, but it also creates shared vulnerability. All life in the universe faces similar risks. This creates a common bond between hypothetical civilizations. If intelligent life exists elsewhere, it likely faces its own cosmic hazards. Gamma ray bursts may have destroyed civilizations we will never know existed. This possibility adds urgency to the search for extraterrestrial intelligence, not just out of curiosity, but out of solidarity. Understanding whether other civilizations exist helps humanity understand its place in cosmic survival patterns. Finally, gamma ray bursts challenge the concept of preparedness itself. How do you prepare for something you cannot prevent? The answer lies in layered resilience. Strong infrastructure, redundant systems, informed populations, international cooperation, long-term planning, scientific research. Preparedness is not a single action. Preparedness is not a single action. It is a continuous process. It evolves with technology. It evolves with knowledge. It evolves with experience. Gamma ray bursts represent one of the ultimate stress tests for planetary civilization. They combine unpredictability, scale, speed, global impact. Few other natural events operate on this level. Understanding them is not optional for a technologically advanced species. It is part of growing up as a planetary civilization. As humanity continues to explore space, build satellites, send probes to distant worlds, and dream of interstellar travel, gamma ray bursts remain in the background. Silent, rare, but real. They do not threaten daily life, but they shape long-term survival strategy. In the final part, we will bring the entire story together and answer the central question. If gamma ray bursts can strike without warning and with unimaginable power, what does that mean for humanity's future? Are we destined to remain vulnerable? Or can intelligence itself become our greatest defense? The answer is not written in the stars. It will be written by human choices. At the end of every discussion about gamma ray bursts, the same question remains. What is humanity's future in a universe capable of destroying entire planetary systems without warning? There is no simple answer, but there is a direction. The future of humanity will not be defined by eliminating cosmic danger. It will be defined by how intelligently we respond to it. Gamma ray bursts represent one of the most extreme expressions of cosmic power. They are reminders that the universe operates on scales far beyond human control. Yet within this reality, humanity possesses something unique: awareness. We can observe distant stars collapsing. We can measure radiation traveling across billions of light years. We can model the effects on Earth before they happen. No other species on this planet can do this. This ability does not make humanity invincible, but it gives us an advantage. The advantage of preparation. The next stage of civilization may involve treating planetary defense as a permanent global priority, not just asteroid monitoring, not just space weather forecasting, but a comprehensive cosmic hazard framework. This would include global gamma-ray monitoring networks, advanced atmospheric modeling, radiation impact simulations, automated infrastructure protection systems, international emergency coordination protocols. These systems would operate quietly in the background, much like earthquake monitoring systems today. Most of the time, nothing would happen, but when something does, response would be faster, calmer, and more effective. Another future direction involves education. A civilization that understands cosmic risk is more resilient than one that ignores it. Teaching basic astronomy, planetary science, and disaster preparedness could become part of standard education worldwide, not to create fear, but to build informed awareness. This changes how people view space, not as distant science fiction, but as an environment that directly affects Earth. Another major element of humanity's future is technological adaptation. Future satellites will be built with stronger radiation shielding. Spacecraft electronics will become more fault-tolerant. Power grids will incorporate protective mechanisms against extreme electromagnetic disturbances. Communication networks will include more redundancy. Cities may incorporate radiation-resistant infrastructure designs. These improvements are incremental. They do not happen overnight, but over decades they accumulate. Each improvement reduces vulnerability. Another possible future path involves decentralization. Highly centralized systems are efficient but fragile. Decentralized systems are more resilient. Distributed energy production, local food systems, regional communication networks, autonomous emergency response units. These reduce dependence on single points of failure. Gamma-ray bursts highlight the importance of this approach. A planet-scale event cannot be managed by a single centralized system. It requires distributed resilience. Another long-term strategy is space-based observation and response. Future space stations and lunar bases could serve as monitoring hubs. Solar orbit observatories could detect radiation events faster. Gravitational wave detectors in space could provide additional data. Artificial intelligence systems could analyze signals in real time and trigger automated safety protocols. This transforms planetary defense from a reactive approach to a proactive one. Another important factor is international cooperation. Cosmic threats do not respect borders. Gamma-ray bursts do not target individual countries. They affect the entire planet. This makes planetary defense one of the strongest arguments for global collaboration. Shared funding, shared data, shared technology, shared response planning. This cooperation could strengthen diplomatic relationships and create new international institutions focused on space safety. It could also reduce competition-driven secrecy in scientific research. Transparency becomes essential. Another possible future development is cultural change. As awareness of cosmic vulnerability grows, humanity may begin to see itself less as separate nations and more as a single planetary community. This shift will not be automatic. It will require leadership, education, and shared experience. But cosmic threats provide a unifying context. They remind humanity that Earth is a shared home. Another future path involves philosophical evolution. Humanity may begin to redefine success, not as infinite growth, not as maximum exploitation, but as sustainable survival. This includes environmental protection, climate stability, resource management, long-term planning. Gamma-ray bursts do not directly relate to climate change, but they reinforce the importance of planetary stability. They highlight how fragile ecosystems can be. Protecting Earth becomes not only about preserving biodiversity, it becomes about preserving a rare, stable platform for intelligent life. Another possible direction is interstellar planning. While interstellar travel remains far beyond current capability, theoretical research continues. Understanding cosmic hazards like gamma-ray bursts is essential for any future attempt to travel between stars. Interstellar missions would require extreme radiation protection, trajectory planning to avoid high-risk regions, long-duration life support resilience. These challenges shape how humanity might approach deep space exploration. Gamma-ray bursts, therefore, influence not only Earth-based survival, they influence the long-term vision of humanity's place in the cosmos. Another important element is generational responsibility. Decisions made today affect the safety of future generations. Investing in planetary defense may not show immediate benefits, but it builds long-term security. This requires political systems capable of thinking beyond election cycles, beyond short-term economic gains. It requires leadership willing to prioritize future survival over immediate popularity. This is one of the hardest challenges in human governance. Another factor is technological ethics. As humanity develops advanced monitoring and defense systems, ethical questions arise. Who controls these systems? How are decisions made during emergencies? How is data shared? How are false alarms handled? Transparency and accountability become essential. Without them, technology can create new risks. Another possibility is the development of planetary-scale engineering. Some scientists speculate about long-term projects such as artificial magnetospheres for Mars or space-based radiation shields. These are currently theoretical, but future civilizations may develop technologies capable of altering planetary environments. Gamma-ray bursts highlight why such technologies may become valuable, not just for colonization, but for protection. However, such power also carries risk. Large-scale engineering could have unintended consequences. This reinforces the importance of careful scientific evaluation and international oversight. Another perspective involves humility. Gamma-ray bursts remind humanity that it is not the center of the universe. Not everything revolves around Earth. Cosmic events operate independently of human existence. This humility can foster respect for natural processes. It can encourage sustainable interaction with the environment. It can reduce the illusion of total control. Finally, gamma-ray bursts challenge humanity to define what survival truly means. Is survival simply continuing biological existence? Or does it include preserving culture, knowledge, and meaning? If Earth were severely affected by a cosmic event, the survival of ideas, art, history, and science would matter as much as physical survival. This is why knowledge preservation projects are important. Libraries, digital archives, underground data vaults, cultural preservation initiatives. They ensure that even if civilization faces disruption, the accumulated wisdom of humanity is not lost. In this sense, survival is not just about staying alive, it is about continuity, passing knowledge forward, maintaining identity, protecting progress. Gamma-ray bursts represent one of the ultimate tests of this continuity. They ask whether humanity can build a civilization resilient enough to survive rare but extreme events, not by eliminating danger, but by understanding it, preparing for it, adapting to it, and learning from it. The universe does not promise safety. It offers opportunity to explore, to understand, to adapt, to survive. Humanity's future will not be determined by whether gamma-ray bursts exist. They already do. It will be determined by whether humanity chooses to become a species capable of facing cosmic reality with intelligence, cooperation, and foresight. That is the real challenge, and it is one that begins now. As the story of gamma-ray bursts comes to its final stage, one last layer remains to be explored. Not the science, not the technology, not even the disaster scenarios, but the long horizon of human existence itself. Because when we talk about events powerful enough to affect entire planets, we are forced to think beyond generations, beyond nations, beyond lifetimes. We begin thinking in terms of civilizations that last thousands, tens of thousands, or even millions of years. And this is where gamma-ray bursts become more than a cosmic threat. They become a measure of maturity. A young civilization reacts emotionally to danger. A mature civilization builds systems that quietly absorb shocks and continue functioning. Humanity today stands somewhere between those two states. We have advanced technology but fragile systems. We have global communication but limited coordination. We have scientific understanding but uneven public awareness. Gamma-ray bursts expose these contradictions. They reveal that technological progress alone is not enough. Survival depends on how that technology is integrated into society. One of the greatest challenges for long-term survival is continuity of knowledge. Civilizations in the past have collapsed not because humans disappeared, but because knowledge systems failed. Libraries burned, records were lost, skills were forgotten. Recovery then required centuries. In a world affected by a large cosmic event, the same risk exists. If satellite networks fail, digital storage becomes vulnerable. If power grids collapse, access to information becomes limited. If communication networks break down, scientific coordination slows. This is why future-oriented civilizations invest in redundancy not just for infrastructure, but for memory. Multiple data storage formats. Physical archives resistant to electromagnetic disruption. Distributed knowledge networks across continents. Offline educational resources. These strategies ensure that even if systems fail, human understanding does not vanish. Another crucial factor is generational planning. Gamma-ray bursts are rare, but they operate on timescales longer than political cycles. Preparing for them requires institutions that can think in centuries, not years. This challenges modern governance. Short-term incentives dominate decision-making. Funding priorities shift rapidly. Public attention cycles move quickly. But cosmic hazards do not follow public attention. They exist regardless of awareness. A civilization that survives long-term cosmic threats must build institutions insulated from short-term pressure. Scientific agencies with stable funding, planetary defense programs protected from political changes, education systems that maintain consistent scientific literacy. This institutional stability becomes a form of planetary armor. Another dimension is technological humility. It is tempting to believe that future technology will solve every problem, but gamma-ray bursts remind us that some limits are fundamental. No material can block unlimited gamma radiation. No shield can stop light-speed energy instantly. No prediction system can foresee every cosmic collapse. This does not make technology useless. It redefines its purpose. Technology becomes a tool for mitigation, not domination. For adaptation, not control. For resilience, not invincibility. This shift in mindset is essential for long-term survival. Another important factor is distributed civilization. If humanity remains concentrated on a single planet, extinction risk remains high. Diversifying civilization across multiple locations reduces total vulnerability. However, distributed civilization must be designed intelligently. Not all locations are equal. Some environments offer natural radiation protection, some orbits provide magnetic shielding. Some planetary surfaces allow underground construction. Future space settlements will need to be selected not just for resources or habitability, but for cosmic safety. This adds a new criterion to exploration. Not just can we live there, but can we survive cosmic hazards there? Another key element is cooperation between science and culture. Scientific knowledge alone does not guarantee preparedness. Cultural acceptance of scientific guidance matters just as much. If societies distrust scientific institutions, emergency responses fail. If misinformation dominates, panic spreads faster than facts. Building long-term trust in science is therefore part of planetary defense. This requires transparency, clear communication, public education, open access to data. When people understand cosmic risk, they respond more rationally. Another challenge is ethical responsibility. If humanity gains the ability to build planetary-scale protection systems in the future, ethical questions arise. Who controls these systems? Who decides how resources are allocated? Who gets priority protection? Planetary defense must avoid becoming a tool of inequality. A truly resilient civilization protects all populations, not just privileged regions. This requires global frameworks and shared governance. Gamma-ray bursts also influence how humanity thinks about progress. Traditional progress focuses on economic growth and technological expansion, but cosmic risk introduces a new dimension. Progress must include survival capacity. Not just faster devices, not just bigger cities, but stronger systems. More redundancy, more adaptability, more stability under stress. This is a different definition of advancement. It values durability over speed. Another subtle implication involves the meaning of exploration. Space exploration is often portrayed as adventure and discovery. Gamma-ray bursts remind us that exploration also means exposure. Venturing deeper into space increases contact with radiation environments. It requires more robust life support systems. It demands greater safety engineering. This does not reduce the value of exploration, it increases its complexity. Exploration becomes not only about reaching new places, but about learning how to survive in hostile environments. Another philosophical aspect is acceptance of uncertainty. No civilization will ever eliminate all cosmic risk. There will always be unknown events, unknown variables, unknown timelines. Accepting this uncertainty is part of maturity. It allows societies to prepare without panic, to invest without fear, to adapt without surrender. This balanced mindset is rare, but essential. Another important factor is intergenerational communication. How does one generation pass knowledge about rare cosmic threats to the next? When no gamma-ray burst has occurred in living memory, awareness fades, preparedness declines. This cycle must be broken. Education systems must maintain cosmic risk awareness even during calm periods. Historical examples show that societies forget disasters over time. This forgetting creates vulnerability. Future civilizations must design systems that preserve memory even when no crisis is happening. This may involve institutional training programs, regular simulation exercises, and cultural storytelling that keeps awareness alive. Another key element is creativity. Survival is not only technical, it is creative. New ideas emerge under pressure, new systems are invented, new ways of organizing society develop. Gamma-ray bursts may inspire innovation not only in science but in governance, education, and social structure. Crisis often accelerates transformation. Prepared societies channel that transformation constructively. Unprepared societies experience chaos. The difference lies in planning. Finally, gamma-ray bursts force humanity to confront a simple truth. Existence in the universe is not guaranteed. Life persists not because the universe is gentle, but because life adapts. Humanity's strength is not invulnerability, it is learning, it is cooperation, it is foresight. It is the ability to turn knowledge into preparation. The universe will continue producing gamma-ray bursts long after current civilizations fade. Stars will collapse, neutron stars will collide, energy will surge across space. These processes are ancient and unstoppable. What changes is how civilizations respond, whether they remain fragile or become resilient, whether they ignore cosmic reality or integrate it into survival strategy, whether they see the universe as an enemy or as a complex environment that must be understood. The future of humanity will not be decided by whether gamma-ray bursts occur. They already exist. It will be decided by whether humanity chooses to become a civilization capable of surviving in a universe that does not care about comfort. a civilization that respects cosmic forces, that plans beyond generations, that builds systems designed not only for prosperity but for endurance. Because in the end, survival in the cosmos is not about avoiding danger forever. It is about building a species strong enough to face it. At the very edge of this story, beyond science, beyond survival strategies, beyond infrastructure and technology, there is one final question that gamma-ray bursts force humanity to confront. What does it mean to exist in a universe that can erase civilizations without intention? The universe does not act with purpose. It does not punish. It does not reward. It simply follows physical laws. Gamma-ray bursts are not evil. They are not disasters in the moral sense. They are natural consequences of stellar evolution. Massive stars collapse. Neutron stars collide. Energy is released. Space is filled with radiation. These events are as natural to the universe as rain is to Earth, but for conscious beings living on fragile planets, these natural processes become existential threats. This creates a strange tension. On one side, the universe is indifferent. On the other, humanity cares deeply about survival, meaning, and continuity. This contrast shapes how civilizations interpret cosmic danger. Some may respond with nihilism, the belief that nothing matters because destruction is inevitable. Others may respond with urgency, the belief that meaning becomes stronger precisely because existence is temporary. History suggests that civilizations that choose urgency over nihilism are the ones that endure. Gamma-ray bursts remind humanity that time is not infinite, not for individuals, not for civilizations, not even for stars. Everything that exists is temporary, but temporary does not mean insignificant. A candle flame is brief, yet it illuminates darkness. Human civilization may be short on cosmic scales, yet it represents a rare concentration of consciousness, creativity, and understanding. This makes preservation meaningful. Another layer of meaning comes from the idea of legacy. What will humanity leave behind? If Earth were affected by a cosmic event far in the future, what traces of civilization would remain? Will future intelligent beings, human or otherwise, discover artifacts of our existence? Will they find records of science, art, and culture, or will humanity vanish without leaving evidence of its achievements? This question has motivated projects that aim to preserve human knowledge beyond Earth. Golden records sent on spacecraft, time capsules buried underground, digital archives designed to last centuries. These efforts reflect a desire not only to survive, but to be remembered. Gamma-ray bursts intensify this desire. They remind us that physical survival is not the only form of continuity. Memory matters, knowledge matters, culture matters. Another important aspect is the responsibility toward future generations. Every generation inherits a world shaped by previous decisions, infrastructure, environmental conditions, technological systems. If current generations ignore cosmic risk, future generations inherit vulnerability. If current generations invest in resilience, future generations inherit security. This creates an ethical obligation, not based on fear, but on stewardship. Stewardship of a planet, stewardship of knowledge, stewardship of civilization. Gamma-ray bursts expand the concept of environmental responsibility beyond Earth. They remind us that Earth's environment is influenced not only by human activity, but by cosmic forces. Protecting the atmosphere, maintaining magnetic field stability through planetary science research, and preserving ecosystems become even more important when cosmic radiation is considered. A weakened environment amplifies vulnerability. A healthy planet increases resilience. Another subtle implication involves humility towards scientific uncertainty. Even the most advanced models cannot predict everything. Gamma-ray bursts challenge scientists to accept limits while continuing to refine understanding. This balance between confidence and humility is essential. Overconfidence leads to complacency. Excessive uncertainty leads to paralysis. Healthy science operates between these extremes, always questioning, always improving. always refining. Another long-term implication involves interspecies survival. If humanity becomes a multi-planet species, different colonies may experience different cosmic risks. Some may survive events that others do not. This creates branching paths of civilization, different cultures, different adaptations, different technologies. Over time, humanity itself may diversify biologically and culturally. Gamma-ray bursts could indirectly shape this diversification by influencing where populations thrive. This adds another layer to long-term human evolution, not just biological, but technological and cultural. Another perspective is existential unity. Cosmic threats do not discriminate between species. If intelligent life exists elsewhere in the universe, it likely faces similar dangers. Gamma-ray bursts may have already destroyed civilizations we will never detect. This possibility adds emotional weight to the search for extraterrestrial life. Finding another civilization would not only be discovery, it would be connection, proof that consciousness can emerge more than once in a dangerous universe. Gamma-ray bursts may also explain why such civilizations are rare or difficult to detect. Survival over cosmic timescales is difficult. It requires not only intelligence, but long-term stability. This reframes the so-called cosmic silence, not as emptiness, but as fragility. Another implication involves the meaning of progress. Progress is often measured by speed, size, and power, but cosmic survival demands different metrics: durability, adaptability, redundancy, resilience. A civilization capable of surviving rare cosmic events is not necessarily the fastest or most powerful. It is the most prepared. This changes priorities. It shifts attention toward sustainability rather than constant expansion, toward protection rather than domination, toward stability rather than endless acceleration. Gamma-ray bursts also reshape how humanity might view risk itself. Modern societies often aim to eliminate risk entirely, but in a universe shaped by extreme events, zero risk is impossible. The goal becomes intelligent risk management, understanding probabilities, preparing responses, accepting uncertainty, balancing ambition with caution. This mindset applies beyond cosmic hazards. It influences climate policy, pandemic preparedness, infrastructure planning, economic stability. Cosmic thinking improves terrestrial decision-making. Another dimension is cultural storytelling. Future generations may tell stories about gamma-ray bursts not only as disasters but as turning points, moments when humanity redefined itself, when planetary awareness expanded, when global cooperation strengthened. Stories shape identity, they influence values, they guide future decisions. Gamma-ray bursts may become part of humanity's shared narrative, not as fear-driven mythology, but as scientific reality integrated into cultural memory. Another final aspect is gratitude. Awareness of cosmic danger can produce appreciation for Earth's atmosphere, for magnetic shielding, for stable climate periods, for the fact that life exists at all. This gratitude can motivate protection, preservation, care, not because of fear, but because of value. When people understand how rare stability is, they protect it more carefully. Gamma-ray bursts ultimately teach one central lesson: the universe does not guarantee safety, but it allows opportunity. Opportunity for life to emerge, for intelligence to develop, for civilizations to rise, for knowledge to accumulate. Whether that opportunity is wasted or preserved depends on choices. Humanity stands at a point in history where cosmic awareness is increasing. We can see distant galaxies, we can detect gravitational waves, we can observe gamma-ray bursts billions of light years away. This awareness brings responsibility to prepare, to protect, to cooperate, to think beyond immediate comfort. In the far future, when humans look back on this era, They may judge it not by how much technology we built, but by whether we recognize cosmic reality early enough to adapt. Gamma ray bursts are not the enemy, they are reminders. Reminders of scale, of power, of fragility, of opportunity. They remind humanity that survival in the universe is not automatic. It is earned through knowledge, cooperation, and foresight. The story of gamma ray bursts is therefore not a story of destruction. It is a story of challenge. A challenge to become a civilization capable of facing the universe as it truly is, not gentle, not hostile, but vast, powerful, unpredictable, and full of possibilities. What humanity becomes in response to that challenge will define its future far more than any single cosmic event ever could. There is one final dimension of gamma ray bursts that goes beyond science, technology, and philosophy. It is the dimension of identity, how humanity chooses to see itself in relation to the universe. For thousands of years, humans believed Earth was the center of everything. Then science revealed that Earth is one planet orbiting one star inside one galaxy, among billions of galaxies. Each discovery reduced our physical importance, but increased our intellectual responsibility. Gamma ray bursts represent the next step in that realization. They show that Earth is not only small, it is exposed to forces that operate far beyond human influence. This forces humanity to redefine what security means. Security is no longer just about borders, armies, or economies. It becomes planetary, atmospheric protection, magnetic shielding, orbital infrastructure stability, space monitoring networks. Security becomes cosmic. This shift will reshape how future civilizations organize themselves. National defense will gradually expand into planetary defense. Space agencies will gain strategic importance equal to traditional military institutions. Scientific cooperation will become as critical as diplomatic alliances. Another major implication is how humanity measures success. In the past, civilizations measured success through conquest, expansion, and accumulation, but gamma ray bursts reveal a deeper metric: survival over long time periods. A civilization that lasts thousands of years is more successful than one that expands rapidly and collapses quickly. Longevity becomes the ultimate achievement. This changes priorities. It favors stability over speed, preparation over spectacle, resilience over dominance. Another consequence is how humanity treats knowledge. In a universe where rare catastrophic events exist, ignorance becomes dangerous. Scientific illiteracy is no longer just a cultural issue. It becomes a survival risk. A population that does not understand basic science is more vulnerable to panic, misinformation, and poor decision-making during crises. Future societies may place even greater emphasis on scientific education, not to create scientists out of everyone, but to create citizens capable of understanding risk, capable of evaluating information, capable of trusting evidence over rumor. This cultural shift strengthens collective resilience. Another long-term implication involves how humanity interacts with technology. As systems become more complex, dependencies increase. Global networks, artificial intelligence, automation. These technologies increase efficiency but also create new vulnerabilities. Gamma ray bursts highlight the need for graceful failure. Systems must be designed to degrade safely, not collapse catastrophically. Future engineers may prioritize modular designs, isolated subsystems, fail-safe mechanisms, manual overrides, offline capabilities. This design philosophy improves resilience not only to cosmic events but to cyber threats, natural disasters, and infrastructure failures. Another important element is cultural adaptation. Human culture evolves in response to environmental pressures. Cosmic awareness may produce new cultural values: respect for planetary stability, interest in astronomy and space science, support for long-term planning. New forms of art inspired by cosmic themes, new philosophy centered on humanity's place in the universe. This cultural shift may influence everything from education to entertainment. Space will no longer be just a backdrop for fiction. It will be recognized as a real environment with real consequences. Another implication concerns human cooperation. Gamma-ray bursts do not allow isolationism. No nation can shield itself alone. Atmospheric effects are global. Satellite networks are interconnected. Supply chains are international. Response requires coordination. This pushes humanity toward greater integration, shared monitoring systems, joint emergency protocols, international scientific institutions. This does not eliminate political conflict, but it creates incentives for collaboration. Cosmic threats provide common ground. Another layer of meaning involves legacy. What kind of civilization does humanity want to become? One that ignores long-term risk in favor of short-term gain, or one that invests in resilience for future generations? This question applies not only to gamma-ray bursts, but to climate change, biodiversity loss, and resource depletion. Cosmic risk becomes part of a broader sustainability framework. Survival is interconnected. Environmental stability, technological resilience, social cooperation, they reinforce each other. Gamma-ray bursts simply highlight the stakes. Another powerful implication is how humanity views exploration. Space exploration often focuses on reaching new destinations, but gamma-ray bursts emphasize the importance of understanding space as an environment. Radiation fields, gravitational hazards, cosmic weather. Future exploration will require environmental mapping of space itself. Just as sailors once mapped ocean currents and storms, future explorers will map radiation zones and cosmic hazards. This transforms exploration from adventure into environmental science. Another perspective involves existential humility. Gamma-ray bursts remind humanity that it is not the master of the universe, but it is not powerless either. It occupies a middle position, not helpless, not omnipotent, capable of learning, capable of adapting, capable of preparing. This balanced view avoids both arrogance and despair. It encourages responsible progress. Another implication involves time horizons. Modern society often focuses on immediate results, quarterly profits, election cycles, trending topics. Cosmic risk demands longer thinking, decades, centuries, millennia. This shift in time perspective is difficult but necessary. Civilizations that fail to plan long-term remain vulnerable. Those that adopt long-term thinking build lasting stability. Gamma-ray bursts encourage humanity to adopt a planetary timescale mindset. Another subtle effect is on human psychology. Awareness of cosmic danger can produce existential anxiety, but it can also produce motivation. Motivation to protect life, to preserve Earth, to invest in science, to cooperate globally. How this awareness is framed matters. Fear-based narratives can paralyze. Knowledge-based narratives empower. This is why communication about cosmic hazards must be careful, accurate, and constructive. Another major implication concerns the future of intelligence. If humanity survives long enough, it may develop forms of intelligence beyond biological limits. Artificial intelligence, neural enhancement, hybrid systems. These technologies could improve prediction, monitoring, and response to cosmic events. They could manage complex data streams, coordinate emergency responses, optimize infrastructure protection. However, they also introduce new risks. Dependence on AI systems creates vulnerability to malfunction. Ethical questions arise about control and decision-making. Gamma-ray bursts therefore intersect with the future of intelligence itself. Another profound implication involves cosmic perspective. Gamma-ray bursts remind humanity that Earth is part of a vast network of cosmic processes. We are not separate from the universe. We are products of it. The atoms in our bodies were forged in stars. The elements necessary for life were created by ancient supernovae. Gamma-ray bursts represent the same cosmic forces that made life possible. This creates a strange symmetry. The universe both creates and threatens life. It is not hostile, it is not benevolent, it is dynamic. Life emerges within this dynamic system. Survival depends on adaptation. Another important realization is that gamma-ray bursts highlight the value of scientific curiosity. Without space telescopes, humanity would not even know these events exist. Without astrophysics, we would be blind to cosmic risk. Science transforms invisible danger into visible knowledge. This knowledge gives humanity agency, not control, but choice. Choice to prepare, choice to adapt, choice to respond intelligently. Finally, gamma-ray bursts force humanity to confront its future narrative. Will humanity remain earthbound and vulnerable, or will it evolve into a resilient, multi-planet civilization capable of surviving cosmic challenges? This is not predetermined. It depends on decisions made today: investment in science, education, infrastructure, global cooperation, ethical governance, long-term planning. These are not abstract ideals, they are survival tools. Gamma-ray bursts are not waiting for humanity to be ready, they exist now. They will continue to exist. The question is not whether the universe will produce extreme events, it will. The question is whether humanity will become the kind of civilization capable of enduring them, not through fear, not through denial, but through understanding, preparation, cooperation, and foresight. That is the real challenge hidden inside gamma-ray bursts. Not the radiation, not the explosions, but the test of whether intelligence itself can rise to meet the reality of the universe it inhabits. And that story is still being written. At the deepest level, gamma-ray bursts force humanity to confront a question that no technology can fully answer. What does it mean to build a civilization that can outlive its own vulnerabilities? Every civilization in history has believed at some point that it had reached stability. Empires rose, expanded, accumulated knowledge, and constructed vast systems of governance and infrastructure. Yet over time, every one of them collapsed or transformed, sometimes through war, sometimes through environmental change, sometimes through internal decay. Gamma-ray bursts introduce a new category of challenge, not political, not economic, not cultural, cosmic. They represent forces that operate beyond human control and beyond Earth itself. They remind humanity that survival is not only about managing internal problems, it is also about navigating an external environment far larger than the planet we inhabit. This realization pushes civilization toward a new phase of maturity, a phase where planetary survival becomes as important as national prosperity, a phase where space is not just explored but actively monitored and understood as part of Earth's environment. A phase where humanity begins to think like a planetary species rather than a collection of competing societies. One of the most important lessons from gamma-ray bursts is the value of anticipation. Most disasters cause the greatest damage not because they are powerful, but because societies are unprepared. Earthquakes kill not only because of shaking, but because buildings collapse. Storms destroy not only because of wind, but because infrastructure is fragile. Pandemics spread not only because of viruses, but because health systems are overwhelmed. Gamma-ray bursts follow the same pattern. The radiation itself is dangerous, but the true devastation comes from systemic vulnerability, weak communication networks, fragile satellite infrastructure, unprotected power grids, uncoordinated response systems. A resilient civilization anticipates these weaknesses and strengthens them in advance. This anticipation does not require fear, it requires responsibility. Another major implication is how humanity defines progress in the age of cosmic awareness. For centuries, progress was measured by speed and expansion, faster transportation, bigger cities, more consumption. But gamma-ray bursts reveal that unchecked growth can increase vulnerability. More satellites mean more exposure. More interconnected systems mean more cascading failures. Progress must therefore be redefined, not as unlimited expansion, but as intelligent optimization, building systems that are not only efficient but robust, designing technology that can operate under extreme conditions, creating societies that can absorb shocks without collapsing. This new definition of progress prioritizes endurance over short-term gain. Another critical dimension is intergenerational continuity. Gamma-ray bursts operate on timescales far longer than human memory. If one generation prepares and the next forgets, vulnerability returns. This creates a need for institutional memory, permanent planetary defense organizations, long-term scientific programs, education systems that preserve cosmic risk awareness, cultural narratives that maintain respect for environmental and cosmic stability. This continuity ensures that preparedness does not fade when danger is not immediately visible. Another layer of meaning involves the psychology of scale. Humans evolved to understand threats at local and regional levels: predators, storms, conflicts. Gamma-ray bursts operate on planetary and galactic scales. They challenge the human brain's natural sense of proportion. This mismatch can cause denial. When a threat feels too large to comprehend, people often ignore it. Overcoming this psychological barrier requires effective communication, using analogies, visual models, clear explanations, helping people understand scale without overwhelming them. This is one of the most important roles of science communication in the modern era. Another implication concerns the relationship between science and governance. Cosmic hazards do not respect political boundaries. Effective response requires coordination between scientific institutions and governments. Data sharing, joint monitoring networks, unified emergency protocols. This cooperation requires trust, transparency, standardized communication channels. Future civilizations may develop planetary governance structures specifically focused on space-related risks, not replacing national governments, but complementing them, creating a layer of planetary coordination dedicated to cosmic safety. Another dimension involves technological foresight. Some of the most important protective technologies do not yet exist. Advanced radiation shielding materials, self-healing electronics, autonomous space monitoring networks, artificial intelligence capable of managing global emergency responses. These technologies require long-term research investment. They may not produce immediate economic returns, but they provide long-term survival benefits. This challenges economic systems that prioritize short-term profit over long-term resilience. Gamma-ray bursts highlight the need for investment models that value future security. Another philosophical implication is the idea of cosmic citizenship. As humanity expands beyond Earth, individuals may begin to see themselves not only as citizens of nations, but as members of a planetary civilization. This identity shift could influence how people think about responsibility. Environmental protection becomes planetary stewardship. Space exploration becomes collective effort. Cosmic risk becomes shared concern. This identity change does not happen overnight. It evolves through education, culture, and shared experience. Gamma-ray bursts contribute to the shift by providing a common reference point, a reminder that Earth's fate is shared by all its inhabitants. Another important factor is creativity and problem-solving. Cosmic challenges require new thinking. Traditional solutions may not apply. Innovative approaches emerge. New materials, new architectures, new governance models, new cultural frameworks. Prepared civilizations encourage experimentation and flexibility. They do not lock themselves into rigid systems. They allow adaptation. Gamma-ray bursts push humanity toward this adaptive mindset. Another implication involves humility in the face of complexity. The universe is not simple. Cosmic events involve extreme physics, multiple interacting variables, uncertainty. Accepting complexity is essential. Oversimplified narratives create false confidence. Accurate understanding requires nuance. This applies to policy decisions as well. Simplistic solutions to complex risks often fail. Effective planetary defense requires multi-layered strategies: technical, social, political, educational. All must work together. Another subtle effect is on long-term cultural values. Societies that value patience, cooperation, and foresight are better equipped to handle rare disasters. Societies that prioritize short-term gratification are more vulnerable. Gamma-ray bursts indirectly encourage value systems centered on long-term thinking. They reinforce the importance of sustainability, not only environmental sustainability, but civilizational sustainability. Another layer involves the concept of hope. It may seem strange to associate hope with cosmic disasters, but understanding gamma-ray bursts can actually strengthen hope. Hope grounded in realism. Not naive optimism, but informed confidence. The knowledge that humanity can detect these events, study them, model their effects, prepare for their consequences. This demonstrates that intelligence itself is a survival tool, not perfect, not absolute, but powerful. Hope comes from the ability to learn and adapt. Another implication concerns cultural memory. Future generations may look back on this era as the moment humanity became truly planetary in its thinking, the moment when space was no longer viewed as distant, but as part of Earth's environment. The moment when planetary defense became a serious scientific discipline. Gamma-ray bursts may be remembered not only as threats, but as catalysts for awareness. Another dimension is moral responsibility beyond Earth. If humanity eventually encounters other life forms, cosmic risk knowledge becomes ethically important. Sharing survival strategies, sharing technology, helping other civilizations prepare. This idea extends planetary ethics into interstellar ethics. It is speculative, but it highlights how cosmic awareness expands moral horizons. Finally, gamma-ray bursts remind humanity that existence itself is extraordinary. Against overwhelming odds, against cosmic violence, against entropy, life persists, consciousness emerges, civilizations rise. This is not guaranteed, it is rare, it is precious, and it is worth protecting. The universe does not promise safety, but it offers opportunity. Opportunity to understand, opportunity to adapt, opportunity to survive. Gamma-ray bursts are part of that universe. They are not anomalies, they are expressions of cosmic reality. How humanity responds to that reality will determine whether it becomes a short-lived experiment or a civilization capable of enduring across cosmic time. And that choice is not written in the stars. It is written in human decisions, in preparation, in cooperation, in knowledge, in foresight. The story of gamma-ray bursts is ultimately not about destruction. It is about what kind of species humanity chooses to become in a universe that demands resilience. And that story is still unfolding. At the very end of this journey, when all the science is understood, all the scenarios explored, and all the strategies considered, one truth remains. Gamma-ray bursts do not define humanity's fate. Humanity's response to reality does. The universe is not gentle. It is not cruel. It is indifferent. Stars explode. Galaxies collide. Radiation crosses unimaginable distances. None of this happens with intention. It simply happens because the laws of physics allow it. And yet, within this vast, indifferent system, a fragile planet produced life that learned to look upward and understand what threatens it. That alone is extraordinary. For the first time in Earth's history, a species exists that can detect gamma-ray bursts billions of light years away. A species that can model atmospheric damage before it happens. A species that can build instruments capable of measuring invisible radiation from collapsing stars. This ability changes everything, not because it makes humanity invincible, but because it gives humanity choice. Choice to prepare instead of ignore. Choice to cooperate instead of compete. choice to build resilience instead of fragile complexity, choice to think long-term instead of short-term. Gamma-ray bursts are not a test of technology alone, they are a test of wisdom. A civilization that prioritizes speed over stability will remain vulnerable. A civilization that prioritizes profit over resilience will struggle to recover. A civilization that prioritizes division over cooperation will fail under planetary scale stress. But a civilization that invests in knowledge, coordination, and foresight increases its chances of survival dramatically. The greatest danger is not the radiation itself. It is complacency. It is the belief that because something is rare, it can be ignored. History shows that rare events shape the future more than common ones. Asteroid impacts reshaped life. Supervolcanoes altered climate. Pandemics transformed societies. Gamma-ray bursts belong to this category: low probability, high consequence, long-term impact. Ignoring them does not make them disappear. Understanding them transforms vulnerability into preparedness. Another essential lesson is that survival is not only biological. Civilization is more than people breathing oxygen. It is knowledge, culture, memory, art, technology. A species that survives physically but loses its accumulated understanding must rebuild from the beginning. A species that preserves knowledge can recover faster, adapt better, and avoid repeating mistakes. This is why information preservation is as important as infrastructure protection. Libraries matter, archives matter, education matters, scientific transparency matters. Gamma-ray bursts remind humanity that knowledge is not a luxury, it is a survival asset. Another profound realization is that Earth itself is a shield. The atmosphere protects life from radiation. The magnetic field deflects charged particles. The planet's position in the galaxy reduces exposure to extreme star activity. Earth is not just a home, it is a protective system. Damaging that system through pollution, environmental destruction, or climate instability weakens humanity's natural defenses. Cosmic risk strengthens the argument for planetary protection. Protecting Earth is not only about saving ecosystems, it is about maintaining a stable platform for intelligent life. Another important insight is that cosmic danger creates shared destiny. No country can hide from gamma-ray bursts. No border blocks radiation. No economy operates independently of global systems. When planetary scale events occur, humanity rises or falls together. This reality encourages a shift from national thinking to planetary thinking, from competition to cooperation, from secrecy to shared data, from fragmented response to coordinated action. This does not mean political differences disappear, but it means survival requires collaboration. Another lesson is humility. Gamma-ray bursts reveal the limits of control. Humans cannot command stars. They cannot stop neutron stars from colliding. They cannot prevent the universe from behaving according to physical laws. But they can choose how to respond. They can design systems that fail safely. They can prepare emergency protocols. They can strengthen infrastructure. They can educate populations. They can preserve knowledge. This is the balance between acceptance and action. Accepting what cannot be controlled. Acting on what can be improved. Another dimension is hope grounded in realism. Not false optimism, not denial, but informed hope. Hope that comes from understanding. Hope that comes from preparation. Hope that comes from cooperation. Human history is filled with examples of adaptation. Humans survived ice ages, they crossed oceans, they rebuilt after wars and disasters, they developed medicine, science and technology. Gamma-ray bursts represent a new category of challenge, but they also represent an opportunity for humanity to mature as a planetary civilization, to move beyond short-term thinking, to invest in long-term survival, to align technological progress with resilience, to build systems that can endure stress, to protect not only present generations but future ones. Another powerful realization is that intelligence itself is rare. The universe contains billions of galaxies, trillions of stars, yet intelligent life may be extremely uncommon. If humanity is one of the few civilizations capable of understanding cosmic danger, that carries responsibility. Responsibility to survive, responsibility to preserve knowledge, responsibility to explore wisely, responsibility to protect the conditions that allow consciousness to exist. Gamma-ray bursts remind humanity that existence is not guaranteed, but they also highlight something extraordinary. Despite cosmic violence, despite stellar explosions, despite radiation storms, life emerged, consciousness developed, civilization formed, science advanced. This is not weakness, it is resilience. And resilience can be strengthened. The future of humanity will not be decided by whether gamma-ray bursts exist. They already do. It will be decided by whether humanity chooses to become a species that prepares for reality rather than hiding from it. A species that values long-term survival over short-term comfort. A species that builds cooperation instead of division. A species that understands the universe instead of fearing it. The universe will continue to produce gamma-ray bursts. Stars will continue to collapse. Energy will continue to travel across space. This will not stop. What can change is how humanity responds, whether it remains fragile or becomes resilient, whether it reacts or prepares, whether it waits or acts. Gamma-ray bursts are not the end of the story. They are part of the environment humanity must learn to live within. And the true question is not, will a gamma-ray burst ever strike Earth? The real question is, will humanity be ready when the universe reminds us how powerful it truly is? That answer is not written in space. It is written in human choices, in science, in cooperation, in preparation, in foresight, and in the decision to become not just a technological species but a resilient one. Because in a universe filled with extreme forces, survival does not belong to the strongest, it belongs to the prepared.